Yeah, good morning. So in the last class, we were dealing with FPGAs, architecture of FPGA, as well as the logical block or logical elements, also called as configurable logical blocks, and along with the IO blocks. So next thing is the IC packages. So these IC packages refers to the materials that contains a semiconductor device. So your whole circuit, your design will be lying on the silicon chip, and that silicon chip will be covered with some material. So that material will be able to contain a semiconductor device. So the package is a case, or like it's a protective box, I can say, that surrounds the circuit material so as to protect it from corrosion or from some physical damage. And this packaging also allows us to mount your electronic component or the IC on the printed circuit board. Okay, so this IC package will be able to protect the IC from the airborne contaminants and provides electrical connections and removes heat also. So we have different types of IC packages. So with different thermal and electrical as well as physical properties. So like as you can see here, I can find dual in package, or I can have SOP, small outline package, or I can have QFP, quad flat package, or I can have QFN, quad flat non-leaded package, or I can have BGA, ball grid array package, and CSP, chip to scale package. So the choice of particular package will be depending upon the number of connections required. So you can go for either DIP or SOP or QFP and so on. That depends upon the number of connections required and the environment of operation of the particular IC. So based upon the environment of operation as well as the number of connection or the number of pins what we have, so you can go for the appropriate choice of the IC package. So this IC is formed to so whatever the IC we have, so that particular IC will be fixed to the bottom of the cavity, and the fine gold wires, or I can go for aluminum wires as well. So the fine gold wires or aluminum wires are connected from the pads of the IC, with the edge of the IC, so like to the points on the package lead frame. Okay, so the metal framework leading to the external package wires, and the cavity is then sealed for the protection. Okay, so we have here the diagrams shown also, so you can observe these diagrams. So for the high count and good package IC, so the use of bond wires will have mechanical problems and delays, and those mechanical problems and delays will be able to reduce the performance of the signals, and the signal will be able to degrade. Therefore, we use the flip chip technology. Okay, so the flip chip, FLIP, flip CHIP, flip chip technology is basically used to avoid the signal degradation due to the mechanical problems and the delays involved in the signal. Like that is, the connection pads on the IC are covered in the conductive material, forming the bumps, like as you can see here. So like these can be called as the bumps, right? So where the connection pads on the IC are covered in the conductive material, okay, forming the bumps. IC is flipped over and fixed on the substrate of the package, and the bumps will be in direct contact with the substrate and the connection points. Okay, so you can take care of this particular figure, as well as you can have different types of packages as shown here, and also you can have definition of the word IC packages. Explain these points. Next concept is PCB. PCB stands for printed circuit boards. So these are used to mechanically support and electrically connect electronic components using some conductive pathways. So these are called as PCB traces. like the conducting pathways, what we can find on the printed circuit boards, so as to have the electrical connection between the different pins and points of the different components are called as the conductive pathways or the PCB traces or the signal traces. And these signal traces are formed by etching the copper sheets laminated onto a non-conductive substrate. So the ICs and different components of circuits are being connected on a printed circuit board, and this PCB will be consisting of the layers of fiberglass. Okay, so we have the use of the fiberglass or any other insulating material, separating the layers of the metal wiring. So the metal is deposited in a layer on a fiberglass, and then uh, and then it is etched away using a photolithography process. So many layers are sandwiched together, and small holes are drilled and coated to form the connection called as vias. Right? So these wires are formed between the layers so as to have the connection between the different components. Yeah, right. So you can have different kinds of PCBs as well. So namely, through-hole PCBs are shown here, and also we have a surface mount PCB. Okay, so you can have the information regarding the through-hole PCBs. So this through-hole PCB refers to the mounting scheme used for the electronic components that involves the use of leads on the components that are inserted into the holes. So as you can see here, so we have the drilling of the holes, and in these holes, the leads of the components will be inserted and drilled into the PCB and soldered to the pads on the opposite side. And I can go for either the manual assembling or hand placement of these components that get soldered, or I can go for a use of automated insertion mount machines. Okay, so this through-hole PCBs, it includes additional coated metal holes through which IC package pins are inserted and soldered, and lead is used to make electrical connections between the pins and the PCB wiring. So this example, you can take it as a dual in package IC, where we have the IC pins on both the sides. Here you can see that we have the IC pins on both the sides of the IC. So this dual in package ICs, they have the two rows of pins, so with 0.1 inch spacing, and they come in small scale integration as well as medium scale integration components. At the max, pins are 48 in numbers. So for more number of pins, so you can use something called as PGA pin. Okay, pin grid array. PGA stands for pin grid array, and it has got up to 400 pins. So these kinds of ICs are used for ICs like the computer CPUs. So whatever the ICs like that are used in the computer central processing unit, and those have got a lot many number of pins. So for example, it's up to 400 pins you can have, and for these kinds of ICs, so you can go for pin grid array PGA kind of IC can be used. So this multi-chip modules are also like a kind of another topology. So we also have multi-chip modules as well as surface mount PCBs. So but here, like we're looking at the through-hole PCBs. Okay. So IC package pins pass through this drilled holes, like as you can see the figure. So we have drilled the holes, and through these holes, the components leads will be inserted, and they will be soldered at the other opposite side of the PCB, either by a manual assembly, or I can go for the use of machines. Okay. Yeah. So after this, you have this surface mount PCB. So regarding surface mount PCB, the components are not directly connected in the holes inserted. Instead, what we do is the components are mounted on the surface of the PCB. Hence the name surface mount PCB. And advantage of the surface mount PCB is reduce manufacturing cost for higher volumes of production. So like here in case of surface mount PCB, electrical components are mounted directly onto surface of a printed circuit board. Okay. An electrical component mounted in this manner is referred to as a surface mount device. So we have the mounting of surface mount devices on the PCB directly. Okay, and it has largely replaced the through-hole technology. So what we have seen earlier, like in the earlier slide, so we saw the through-hole technology. So where we have the additional coating metal holes through which the IC package pins are inserted. So when compared to that, this surface mount PCB has largely replaced the through-hole technology construction method of fitting the components onto the PCB. And it allows for more components to fit on a given area of substrate. Okay. Yeah. So this, yeah. Like in this case, surface mount PCB. So the solder paste is applied between the pins and the pads and melted, and this will be forming as the connection. Like using the soldering gun and the paste, and I'll be able to have the connection to be established. Example for surface mount PCB are shown in figure. So we have something called as QFP. QFP stands for quad flat pack. Here it is. So quad flat pack, you can see where we have the pins on all the sides of the IC. Quad flat pack QFP. These have pins along all the four sides and suitable up to 200 or more number of pins. And the spacing among these pins will be 1 mm to 0.05 mm. So for high pin count packages. So after this you have multi-chip modules, called as MCMs, multi-chip modules. So this multi-chip module is an electronic package consisting of multiple number of integrated circuits or ICs assembled into a single device. So this multi-chip module attains the bare chip to a ceramic substrate rather than placing each IC in a separate package and assembling many packages onto a PCB. So the module can be encapsulated or packaged by a plastic molding and is mounted on the PCB. So these multi-chip modules offer better performance and can reduce the size of a device. So the resistors and capacitors are also printed and soldered to substrate, and a complete module is then encapsulated. So with external connections made through the package pins on a PCB. And this is ideal for high density. Example are the cell phones. So you can see in the figure a ceramic multi-chip module containing 4 power pi processor dies. Okay, and they have 4 36 MB L3 level 3 cache dies. Okay. So next is the signal integrity. So we can have a definition of signal integrity as the ability of an electrical signal so as to carry the data or information reliably and avoid the effect of high frequency EMI, electromagnetic interference from nearby signals. Okay. So the signal integrity will be leading us to the reduction in the voltage levels. So like if you see the propagation delay in case of PCB trace, okay, so when each wire connection is used on a PCB so as to have the connection between one point to the another point, so the speed of signal is very important. Okay, so the signal trace that is used to have the connection between one point with the another point on the PCB track. So the speed with which the signal is moving is very important. And in case of a common PCB material, so the speed will be almost equal to half of the speed of the light in the vacuum. Okay, remember this. Like in a common PCB material, the speed of the signal travel will be almost equal to half of the speed of the light in the vacuum. Right? Hence we have the formula 1 by 2c. Okay, so where this c is nothing but the speed of the light in vacuum, that is equal to 3 into 10 to the power of 8 millimeter per second. So half of it is 150 millimeter per nanosecond. So the designers will use this particular formula, okay, while designing the circuits. So this won't affect much for a simple circuit. So, but if you are having a larger design, larger huge PCB, like there will, like in that case, we need to take care of the total path delay in high speed designing. Okay, so like in case of high speed designing, so this propagation delay does matter, and in case of a simple circuits, we don't need to have worrying much about this. So when we talk about the signal integrity, so we have basically two problems encountered. Okay, so one we call it as the ground bounds. Okay, right, and second one is nothing but the AMI, electromagnetic interference. So first, let me see the definition for this ground bounds. So like when we talk about this ground bounds problem, so when we have a transient current flow, so the output will be switching levels. Okay, so when the output is able to have switching from low to high, or from low to high to low, or from 0 to 1 or 1 to 0. So when we have this transient current flow, it may give rise to the inductance. Like as you can see here, so we have the formation of inductance here and here. Okay, so you can see in the figure. So that unintentional formation of inductance will be there, like near this plus VCC and near the ground. Okay, so we have a formation of so these unwanted unintentional formation of inductance, like near the VCC and near to the ground. So the plus VCC inductance is because of this bond wire, okay, and the PCB inductance. Similarly, like at the ground also, so when the level changes, like this transient current flows and the inductance comes into picture. Shown that. So when the logic level of signal is switching from either 0 to 1 or from 1 to 0, so this inductance will come into picture, and this is not intentionally designed. Okay, so like these are the unwanted, undesired formation of inductance. So one at the plus VCC point and another at the ground point. And these are called as parasitic inductance or unintentional inductance. And this will spikes on the further drivers. So because of this, the threshold voltage of the device may be varying. So because of these parasitic inductance, right, induced because of the transient flow current. So when the logical levels will be switching, so like this we call it as the ground bounds. Okay, and we cannot ignore this ground bounds problem. Why? Because it may be affecting, or it will cause the variation in the threshold voltage of the devices. Okay, so we can have the solution for this ground bounds problem. So one such solution is the use of the bypass capacitors. Okay, we can go for a use of the bypass capacitor, like in between the ground point and the plus VCC. So say like of the value 0.01 to 0.1 microfarad and close to the package pins. So such capacitors will be holding the charge that can quickly supply the need for supply drivers, and this will also avoid the spikes. Okay, why? Because the spikes, like these spikes are the main cause for this formation of unwanted unintentional formation of inductance, like so-called the parasitic capacitance. Hence, by avoiding the spikes by the use of this bypass capacitor, so we can have the solution as the minimization of the ground bounds problem. Second solution is so you can go for the use of separate PCB planes. As you can see here in the figure, so you can go for a use of separate PCB planes, one for the ground and one for the plus VCC. So this inductance problem doesn't come into picture here. Okay, so we have here the signal layer, like on the top and the bottom layer, like we have signal layer. and we have this the one plane for power and one plane for the ground. So you can go for separate planes, one plane for the power line and one for the ground line. Okay, so by having separate PCB planes, one for the ground and one for the VCC, so we can have the minimization of the ground bounds problem. And so for like one more solution can be to have the limit of the slew rate. So what is slew rate? Basically dV naught by dt, like expressed in volt per centimeter or say volt per microsecond basically. So this the rate of change of output voltage with respect to the time, we call it as the slew rate. So by limiting the output slew rate also, you can have the minimization of this ground bounds problem, because suppose if the change is more, means we have more and more formation of inductance. So but if the voltage change is less, so then inductance doesn't come into picture at all. So but I suppose if I limit this slew rate, means this will make the speed of the operation slow. Okay, why? Because the basic definition of slew rate says the rate of change of output voltage. Okay, and if the slew rate itself is limited, means the speed of operation will be also becoming slow, obviously. Therefore, we have a trade-off between the propagation delay and the speed of operation and noise handling. Okay, so based upon the application, I can need to select either I can go for the reduction of propagation delay, or I can achieve higher speed of operation, and I can have the handling of noise effectively. Okay? And that is the selection among the noise handling as well as the speed factor will be the main criteria here. So basically, like we have seen the solution of this ground bounds problem, as I can go for a use of the bypass capacitor, look up the value 0.01 microfarad to 0.2 microfarad, okay, between the ground lines and the plus VCC lines. Okay, or I can go for a use of separate PCB planes as shown here, where I'll be having a separate plane, one meant for power line and separate plane, one meant for the ground line. Or I can go for the third option as well, where I'll be limiting the output to slew rate. Okay, so here we have right. So this occurs when the rise time is comparable with the path delay. So yeah, minimization of ground bounds is over. So next is yeah, electromagnetic interference. So electromagnetic interference is so basically the disturbance what is caused. So the disturbance caused by the electric field, okay, electromagnetic field, so which holds up for proper performance of an electric device. So this will be acting as a hurdle so as to have the effective performance of the electrical device. So this EMI can come say from man-made noise or from natural sources of noise such as sun or the earth magnetic fields. So the transition caused is due to the electromagnetic fields that will be interfering with the signal. Okay, so like when we have the energy radiated from the PCB traces, it also give rise to the EMIs, electromagnetic interference, and it can induce noise in the other systems as well. So we have a limitation on how much of electromagnetic interference can be accepted. Okay, so we have the first cause of this EMI is energy radiated from the PCB traces. Okay, and so we have this crosstalk as well. So where crosstalk can be defined as the unwanted transfer of signals between the communication channels. Okay, like it may give rise to crosstalk. So we also must see how much of this crosstalk is allowed. Okay, yeah. So next heading is the differential signaling. So this differential signaling can be defined as the method for electrically transmitting the information or the data using two complementary signals. Okay, here we have the use of say two complementary signals. Okay, like it involves both transmission of plus signal, so called SP. Okay, so where SP is the positive signal, and its negation as well, right? Or it's a negative signal as well, represented by Sn. Okay, so this differential signaling is basically a method of transmitting the information using two complementary signals. One is the positive signal and one will be the negative signal. Okay, namely SP and Sn. Okay, so the like this technique will be able to send the same electrical signal as a differential pair of signals. Okay, each in its own conductor. Okay, so this differential signaling will be able to reduce the system susceptibility to the noise, and it involves transmitting both kinds of signals, namely the positive signal SP as well as its negative signal Sn. Okay, and sensing the voltage difference between the two signals at the receiver end. Okay, suppose if I assume that SP minus Sn, okay, so the positive signal minus negative signal is a positive voltage. So then this S is transmitted as a value 1. Okay, and if I assume that SP minus Sn is a negative voltage, means this S will be transmitted as a value 0. Okay, I repeat, suppose if SP minus Sn is a positive voltage, or the difference between the SP minus Sn is a positive voltage, means this particular S factor will be transmitted as a value 1. And if SP minus Sn is a negative voltage, right? So then this S will be transmitted as a value 0. Okay, so this arrangement is as shown in the diagram. Okay, so the noise is induced equally on both the lines, right? SP line as well as the Sn line. So such common mode noise is cancelled out. So when the difference in the voltage is being sensed. Okay, suppose a noise voltage B noise is induced, okay, equally on the two wires, okay, at the receiver end. So then the voltage sensed will be SP plus V noise minus Sn plus V noise, and that will be giving us SP minus Sn. Okay, so for the assumption of the common mode noise, the differential signal must be routed along the parallel paths of a PCB. You can see that the signal are inverse of each other. Okay, this means what? That both signals are able to change at the same time. So the cross talk can also be cancelled out. So the different signaling allows common mode noise rejection as well, and it can have the improvement in the signal integrity. So again, signal integrity basically means that I'm supposed to have the reduction in the ground bounds, and I'll be able to reduce the crosstalk and reducing the switching current and reducing the electromagnetic interference. Okay. Yeah. So like this is the summary of the whole topics what we have covered. Actually, like we saw that we have an initial implement in IC technology, IC manufacturing process, and we're able to embed more and more components like inside a small silicon area. Hence, the whole size of the component, size of the module, and the whole size of the circuit itself is becoming miniaturized. And when compared to the olden days, nowadays we have smarter and smaller devices available in the market. And we have seen the different logical families as well, like starting from SSI, MSI, LSI, VLSI, ULSI, and TTL logics as well. And we have seen the basic information regarding the ASICs and full custom, semi-custom, standard cell. And we have the architecture details of this PALs, programmable array logic, and PALs, FPGAs, and the various IC packages available. So for PCB assembly, like namely the through-hole and the surface mount PCBs. And lastly, we have seen the different signaling as well as the signal integrity. So like this finishes the module 1. And I'll be starting with the module 2 in the next video. Thank you.